Good afternoon, everyone. I hope you are all doing well. Just wait for a few minutes so that everyone will join, and then we'll start the meeting. So I hope you have gone through all the four lectures and have the good basics. So today we'll be completing von Haber cycle, and what we're learning in the previous class about the enthalpy of atomization, right? Enthalpy of the reaction, these things like enthalpies of the reactions we have seen. So that will be coming to von Haber cycle at last. So I didn't give any homework in the last class, right? So no issues. Okay, then let's start. No. First thing we are going to see today is lattice energy. And after lattice energy, we'll be seeing hydration energy. Hydration energy we'll be seeing. And after seeing these, we'll be seeing how we are going to calculate the lattice energy using Born-Haber cycle and how we can use Born-Haber cycle to calculate different types of energies. Generally, what is the main case is that as we cannot directly find out lattice energy of a crystal, so what we do will be taking the single steps of a reaction. Nothing but how the crystal is first converted into a gaseous molecule or any other individual atom, and after that individual atom, if it is losing an electron, like Na is losing electron and it is giving us Na plus. No, that is nothing but ionization energy, right? So, and chlorine is gaining one electron, that is nothing but electron gain enthalpy. So we'll be uh, adding all the summing up all those individual energies, and then we'll be deriving lattice energy indirectly. So based on this, many questions are given. Generally, all the values will be given. Any one of the value will not be given. Just you need to see which one you need to take minus, which one you need to take plus. That's the only thing. What is the conversion is the main thing. Like they'll be giving you the ulta values. They may be giving the opposite values, and you need to take the right values. So try to see what are the values they are giving, whether it is a formation reaction or decomposition reaction. Based on that, change it. The enthalpy is exothermic or endothermic. That's the only point. No. For today, let's see what is lattice energy first, represented as delta H lattice. No. Energy required to completely separate. No. This is nothing but energy required to completely separate 1 mole of solid ionic compound into gaseous ions. Now let's say we are taking 1 mole of NaCl crystal, 3D crystal. We are taking this 3D crystal and we are disintegrating it totally into all into n number of Na plus ions and n number of Cl minus ions. This is what we'll be doing. Now to convert this perfectly structure into these individual atoms, we need a lot of energy. Okay, we need a lot of energy. Sorry for that. We need a lot of energy. So this energy is nothing but lattice energy. Okay. So we cannot directly do that. So what we'll do, we'll directly calculate it indirectly using von Haber cycle. Okay. Let's see this more clearly. Now let's see this is our 3D crystal and it is consisting of purple ones as sodium and these green ones as chlorine. Okay. These green ones as chlorine and these purple ones or pink ones as sodium. Okay. Now this is a perfect crystal. There are interactions all in 3D space, right? On all the sides, there is some kind of attractions and repulsions. So here they are very much stable. And now what I'm doing, I'm breaking all these attractions and making it into single atom. That means I'm breaking good bonds, like good interactions, right? So what is happening? I need to provide energy to break such kind of good interactions. If I want to break a bond, I need to give energy, right? Why? Because the attractions are very high. That is the main reason why a bond is formed. And if I want to break those attractions, I need to give some energy so that they'll go far apart from each other. The same thing we are doing here also, where I'll be providing certain amount of energy for this 3D crystal and it will be converted into gaseous ions or any other solid ions. Gaseous ions. Now this energy, how much I am giving. This is nothing but lattice energy. Okay. In this way, we'll be converting it into single crystals, single atoms. This is nothing but lattice energy. Okay. Are you clear with this? If you have any doubts, you can clarify it. Now, for your example, whenever you are converting a NaCl solid into Na plus and Cl minus gaseous atoms, the lattice enthalpy is plus 787 kilojoules per mole. Very high, right? Now, is this endothermic or exothermic? Now, you can see the positive sign, right? We are breaking a lot of bonds. In a three-dimensional, we are breaking a lot of attraction. So, we need to provide a lot of energy. 787 kilojoules per mole is a very lot of energy. This is very much endothermic reaction. No. Next, first thing, what is happening during this process? Energy is being absorbed, right? Yes or no? Energy is being absorbed.
Chemistry.
During this process, what is happening? Energy is being absorbed, right? To break the crystal, we need to provide the energy so that the interactions between sodium and chlorine ions are broken and Na plus and Cl minus ions are given out. Clear, right? Now, for 1 mole of ionic compound, now it gives rise to its constituents gaseous ions. Now, what is happening when you are converting this 3D crystal into gaseous ions? We are breaking the ionic interactions, right? And next, what we have seen, this is a endothermic process. Why it is endothermic process? As Na and Cl minus ions. Let's take one Na plus and how many Cl minus ions are surrounding it? It is surrounded by all sides, on all the sides, front, back, side, left, right, and above and below. All the sides there are chlorine atoms around the sodium atom. That means how many interactions it is having? 6 interactions, right? No. 6 interactions it is having. That means you need to break 6 attractive forces. That means you need to provide certain energy, right? That is the only reason why lattice energy is endothermic reaction. Okay. Now let's say the opposite case. Energy is released. What does that mean? Nothing but whenever the gaseous ions are converted into solid. Whenever you are taking gaseous ions and arranging them in a particular 3D fashion so that it is giving rise to a crystal. This is the exact opposite of what is we are talking about lattice energy, right? Now what happens here? Ionic bonds are formed. If ionic bonds are formed, that is, they are very strong interactions. That means the reaction will be exothermic or endothermic. The reaction will be exothermic, right? Why? Because the bonds are formed and energy is released due to stability. Clear with this, everyone? Any questions? Okay. If you have no questions, I'll be moving forward. No. We have seen lattice energy, right? What is the lattice energy? Nothing but we are converting a solid crystal into gaseous ions. This is done until some part. Now, after, let's say we are taking these gaseous ions and we are dissolving it in water. Now, whenever NaCl solid is there, we are converting into Na plus and Cl minus gaseous ions, right? This is nothing but lattice energy. Lattice enthalpy, right? Sorry for that. This is nothing but lattice enthalpy, right? So whenever this Na plus ion and Cl minus ion are dissolved in water, what happens? As they are cation and anion, and water molecule, what does water molecule have? Does it have any dipole? Right, it has a dipole, and due to this electronegative difference, what happens? Hydrogen will getting partial positive and oxygen will be getting partial negative, right? So whenever a cation is there, the partial negative of the oxygen will be surrounding the cation and partial positive of hydrogen will be surrounding the anion. Now what is happening whenever you are dissolving these gas ions in the solvent? What happens? There are some type of bondings due to this difference in the electronegativity difference between oxygen and hydrogen as well as ions which we are taking. Now, due to these interactions, how many interactions are there in this diagram for Na and oxygen? There are three interactions. That means there are three new attractive forces. That means again, three energies will be released. Clear with this? As the number of interactions, number of oxygens surrounding the sodium increases, the number of energy will be increasing. That is hydration enthalpy for this sodium atom will be increasing. Now, as chlorine is surrounded by hydrogens, as the number of hydrogens surrounding it, chloride ion increases, the hydration energy again increases. That's the only thing. You need to see how many interactions are there. As the interactions increase around the cation or anion, the hydration enthalpy increases. Now, tell me, is this chlorine ion and chloride ion and sodium ion same? No, right? But they are both different. They have different sizes and a lot of them are different. They're not same. So that's the reason the hydration sphere, like how many water molecules are surrounding around chlorine atom is different. How many water molecules are surrounding around sodium atom is different. So both of them have different hydration enthalpy. If we mm, uh, combine them together, it gives us hydration enthalpy of Na plus and Cl minus. That is NaCl. Okay. Now let's see briefly what is the definition of hydration enthalpy. First thing, enthalpy change when 1 mole of gaseous substance or ions is completely hydrated by large amount of water. Okay, large amount of water to form aqueous ions. That's the main thing you need to see. You took some ion and dissolved it in solvent. Now that had some interactions with the water or with the solvent we have taken. Now those interactions will release some type of energy. If in case of water, we'll call it as hydration enthalpy. Okay. Now this is a small reaction again we'll be seeing, that is sodium cation is there. Sodium cation is there in gaseous form and we are adding the solvent, that is H2. Now what did I say? Now this is a free gaseous atom. After adding water, what happens? These negative dipole as well as positive partial charges are surrounding the cation. Now, the negative will be surrounding the cation, right? Yes or no? Negative will be attracting positive, positive will be attracting negative, the same thing. Now, as we are using a cation, that is sodium cation here, the negative charge, that is oxygen, which has partial negative charge in water, will be surrounding the cation. Now, this is nothing but the hydration sphere. How many are surrounding the cation? That we'll call it as hydration sphere. Hydration sphere. Okay. As the hydration sphere increases, the hydration enthalpy increases. Clear, everyone? No. If you see here, the hydration energy for sodium, it is given as minus 406 kilojoules per mole. That is very much high, right? So these type of terms you need to see when it will be exothermic, when it will be endothermic. That's the only thing. No need to remember the numbers here. So why it is exothermic? The only reason is whenever we are dissolving the cation in water, due to the attractions between the cation and the solvent molecules, there will be release of energy. This release of energy is nothing but exothermic reaction. Clear? Due to attractions, because this interactions only between positive and negative charges, energy is being released. Now, whenever we add the anion also, the same thing will happen. Now, if we combine both anion as well as hydration energy of anion and hydration energy of cation, we'll get enthalpy of solution. Okay. Now, what is enthalpy of solution? Enthalpy change when 1 mole of substance dissolved in specified amount of solvent. Here we are changing solvent. We are saying specified amount of solvent. We are not using a lot of solvent. We are taking a specified amount of solvent and we are checking what is the enthalpy of solution under constant temperature and pressure. Now, if you see here, first thing, ionic lattice is there. How does it present? It is present in 3D structure, three-dimensional structure. Now, if you see a crystal cube or sugar cube or salt cube, will it have a deformities? No, right? It will look like a perfect crystal. That's what we are talking, like a 3D object. Now, first thing what I'm doing, I'm going to break them into gaseous state, gaseous ions. Clear, everyone? This, when we are converting this 3D crystal into gaseous ions, we'll call it as lattice enthalpy. We are not talking about enthalpy of solution now itself. Yeah, first I'm going to create or take gaseous ions from the solid crystal. That is called as lattice enthalpy. Now, after getting gaseous ions, what will I do? I will be dissolving them in a solvent now. Now, if I dissolve it in solvent, these ions will be having interactions with water molecules. Now, how many water interactions they are having based on the different amount of energy is released with respect to cation and with respect to anion. They have both have different type of hydration spheres. Okay. Now, based on, let's say this is having now four hydration, like four water molecules are said. Let's say four hydration. Four is the hydration sphere. Now, here also four is that. Now, as the interactions are same, let's just generally assume the energy evolved is also more. Energy evolved is also same. Now, if I say there is one more water molecule here, minus and plus. Now, that cation has 5 interactions with water and anion has 4 interactions with water. Now, here the hydration energy given by cation is more. That's the only thing. We cannot say every time the cation and anion will be having same hydration sphere. Based on the charge present on cation and charge present on anion, the hydration sphere may change. Okay. It is not exactly equal. It is truly based on, only based on what is the positive charge, what is the negative charge. If positive charge is more, attractions will be more. If negative charge is more, attractions will be more towards positive charge. That's the only point you need to remember here. Now, if I see enthalpy of solution, whenever I add a solid salt cube to water, what happens? First, the solid salt cube will convert into ions. Now, to convert this solid salt cube into ions, what energy we require? Nothing but lattice energy, right? Lattice energy is required. Now, after converting them into gaseous ions, these ions will be dissolved in aqueous medium, that is water. Now, whenever these are dissolved in aqueous medium, it is called as hydration energy. Okay, hydration energy. Now, hydration is nothing but sum of hydration energy of cation as well as sum of hydration energy of anion. That is what we are writing here. Hydration enthalpy of solution is nothing but the summation of hydration lattice enthalpy plus hydration enthalpy of cation plus hydration enthalpy of anion. Why we are writing cation and anion differently? Because both have different hydration spheres, and as the interactions increase, hydration energy also increases. Now, in this case, cation is having 4 interactions and anion is also having 4 interactions. So that we can say cation and anion may have equal hydration energy. If the cation is having one more, here the hydration energy released by cation is more when compared with hydration energy released by anion. The only thing you need to see that. As hydration sphere increases, hydration energy increases. Now, for dissolution, if delta H solution is less than 0, what does that mean? It is a spontaneous process. We'll be seeing what is spontaneous process. Now, when does this reaction? Nothing but negative, right? If it is negative, what is this? This is a exothermic or endothermic reaction. It is a exothermic reaction. If delta H is negative, we'll call it as exothermic reaction. And if you want to get delta H as negative, now tell me, what did you learn? Whether lattice energy is exothermic or endothermic? Answer in the chat. Whether lattice energy is exothermic or endothermic. If it is exothermic, enter exo. If it is endothermic, enter end. Class, lattice energy is exothermic or endothermic? Yeah, you are right. You are right. No, lattice energy is endothermic, right? Why it is endothermic? Generally, we are disturbing the 3D crystal and making into ions, right? This requires energy to break the bonds. That is the main reason why lattice energy is endothermic. Now, whenever we speak about hydration energy, there are new bonds formation between the ions and water molecules. Now, because this attractive forces or hydrogen bondings or dipole-dipole interactions, what happens? Ion dipole interactions, what happens? Energy is released. Generally, these interactions are exothermic reactions. Now, if you want to keep delta H solution as a negative, what does that mean? Exothermic reaction should be very much high. That means the solution should be exothermic. The No, delta H lattice is generally endothermic reaction and delta H hydration is generally exothermic reaction. Are you clear with this concept? Why lattice energy is endothermic and why hydration energy is exothermic? Oh, if you are clear, then let's move to next thing. That is, whenever hydration energy is greater than lattice energy, then only the solution enthalpy is very much high, and that is exothermic. Clear? No. Solubility of ionic compounds. When it is soluble, whenever the hydration energy is very much greater than lattice energy, then only the salt or whatever solid you are adding to the solvent is soluble. Okay. Now the hydration energy should provide enough enthalpy so that it can overcome the endothermic process, that is lattice energy. Okay. That then only the reaction can happen smoothly. Now, if you see in that way, that means lattice energy generally it should be less and hydration energy generally should be high. So the reaction will be happening spontaneously. Now decrease. Now what are we talking about? Nothing but solubility of an ionic compound will decrease with increase in lattice energy. What does that mean? Nothing but as the crystal is becoming strong and strong, the dissolution power will decrease. The solubility of that crystal in solvent will decrease. Simple concept. Now, if we talk about hydration energy, as hydration energy increases, dissolution will increase. Why? As it is exothermic reaction, whatever energy is released will be utilized to overcome the lattice energy. To overcome the lattice energy, so that the reaction will happen spontaneously. No. If you understood the concept, try to do this question quickly and answer in the chat. I'm giving a few minutes. Try to answer in the chat. The lattice enthalpy of AB2 is 1600 kilojoules. Okay. He's saying lattice enthalpy of a crystal is 1600 kilojoules. If hydration enthalpy of A2 plus a cation has minus 800 kilojoules per mole and B minus anion which has minus 500 kilojoules per mole respectively. Now he's asking whether AB2 is soluble in water or not. What you need to remember here? Nothing but delta H solution should be negative if you want the AB2 should be soluble in water, right? Now, if that's the point, nothing but what you need to do, summation of the hydration energy of anion and cation should be more than the lattice energy, that is more than 1600. That's what you need to see. Now do it, let's do it stepwise. Yeah, you are right, you are right. Now, if you see this, delta H lattice energy of AB2 is given as 1600 kilojoules per mole and hydration energy of A2 plus ion is given as minus 800 kilojoules per mole. And for anion B minus, the hydration energy is given as minus 500 kilojoules per mole. But whenever AB2 is dissociating, whenever AB2 is disturbed, how many ions are given? A minus, A plus, A2, sorry, A2 plus and 2B minus. So he's saying that for one ion of a cation, now the hydration energy released is minus 800 kilojoules. Now for one anion, that is B minus, the hydration energy released is minus 500 kilojoules. Now how many B minus ions are there? Two B minus ions are there. That means two times of the B minus ions hydration energy is released. Okay. Now if we write delta H enthalpy of solution, nothing but lattice enthalpy plus hydration enthalpy of cation plus as we have two anions, as we have two anions, we'll be adding two times of hydration enthalpy of one anion. Clear with this? How we are writing the formula? No, nothing but substitute the values directly. 1600 plus minus 800 plus 2 into minus 500. That gives you minus 200 kilojoules per. Now tell me whether it is soluble or not. As delta H solution is exothermic, that means the salt is or the crystal is soluble in the solvent. Now, next we'll be seeing enthalpy of dilution. What is dilution? Now, dilution is a process where we'll be taking a particular molarity of a solution and we're adding extra amount of solvent. We are adding solvent here, not solute. Here we're adding solvent so that there will be dilution. Now, as we are diluting, what happens? The solvent molecules increase. That means the solvent molecules which are interacting with the anion as well as cations present in the solution are increasing. Generally, what happens as the interactions increase, enthalpy also increases. That's what we'll be going to see in enthalpy of dilution. Enthalpy change associated with addition of specified amount of solvent in a given concentration of substance. What does that mean? Nothing but he's saying that how much amount of enthalpy is released whenever you are adding, let's say, 500 ml of solvent and whenever you are adding 1000 ml of solvent. What is the change? What are you going to observe? Now, as I said, as the interactions increase in between the solvent and the ions that are solute, now as the interactions increase, what happens? Enthalpy will also increase. The energy released due to the formation of new bonds will increase. Now, what is first of one? That is amount of solvent we need to see. Second thing is what is the concentration of original solution comparatively saying what happens to the enthalpy. Now next thing, as the interactions increase, nothing but it is normally a exothermic reaction. Clear, right? If you have any doubts, try to mention in the chat. No. Whenever HCl is, let's say I'm taking HCl and dissolving it 10 moles of the aqueous solvent. Then what happens? HCl will bond with exactly one H will and one Cl minus will be given out and they will be interacting with all the 10 aqueous molecules. As I increase it to 25 molecules, it will interact with 25 molecules. So because of that, what happens? The enthalpy as the interactions increases, the enthalpy also increased. Okay. Now, as I go to infinite dilution, the enthalpy also will increase in the same way. It will not be infinite enthalpy, but there will be a particular point where the interactions around the cation will limit. So at that point, the increase in enthalpy will also stop. Okay. Now, let's say you are there and surrounding you, only 10 people are possible. After 10 people, if I'm giving the 11th one, as there is no space between those 10 people, this 11th person can come inside, right? So the same way here, whenever Cl minus or H plus is formed, now on the sole space, the ions will be surrounding, the aqueous molecules will be surrounding, right? After some amount of molecules surrounding it, then there will not be any space for the another water molecule to or attract towards the H plus ion. So at that time what happens after certain point of dilution, the enthalpy increase will not be there. Okay. Now, Born-Haber cycle, very much important. Simple questions will come directly in JEE or in your CBSE also. What you need to do, just to see what are the values given and try to see how you need to use them in the formula. Okay. Now, in Born-Haber cycle, what we'll be doing, first thing we'll be using to calculate enthalpy of complex reactions. So Born-Haber cycle is nothing but, in case of lattice energy, let's say, whenever we are taking NaCl and converting into Na plus ion and Cl minus ion in gaseous state. So we cannot directly get the calculation here. What we'll be doing, first thing we'll be getting as Na solid and Cl2 gas. This is a normal state of the standard ones, right? Chlorine exists as gas and sodium exists as solid. This is what we see generally. What we do first, we'll convert the 3D into this normal basic standard ones, and then we'll be converting sodium solid into sodium gas, and then we'll be converting into sodium solid into sodium gaseous ion, and then solid gaseous ion to Na plus. What we are doing, we are removing one electron. If you are removing one electron, what is this energy called as ionization energy? So what we'll do, instead of going through a direct complex step, what we'll do, we'll divide the steps individually, step 1, step 2, step 3, so that it is easy for us to calculate the enthalpy value overall for the reaction. Okay. Now, what we do, break down into simpler standard reactions, simple reactions, so that we can find out the values. After that, we'll be applying the Hess law. Nothing but what does Hess law say? If you take enthalpy of a complex reaction and if you divide it into 100 steps or 50 steps, if you sum up all the enthalpies, it will give up the enthalpy of that particular complex reaction itself. That doesn't give any different value. Now, for now, let's try to calculate for NaCl, how we are going to take. Whenever you take NaCl solid, then what are the steps you follow until it is converted into gaseous ions or until it is converted into an aqueous solution. Okay. First thing, let's see lattice energy. Lattice energy, nothing but when we are converting NaCl solid into Na plus ions as gaseous state and Cl minus ions as gaseous state. Okay, this is nothing but our lattice energy. This is what we need to find out. So what we do to find out, we cannot do it directly. So what we do, we differentiate them into smaller step 1, step 2, and step 3. Okay. First thing, we'll be converting NaCl solid into Na and Cl gas. You know, no, this is what nothing but formation reaction enthalpy. Okay. Next, as we got them, then what I am doing, I'm converting the solid Na into gas. Whenever solid is directly converted into gas, what we'll call it as sublimation, right? So we give the name sublimation enthalpy directly. Now, whenever we are doing for it for gas into gaseous ion, so nothing, right? Then Na is converted into Na plus ion where one electron is removed from sodium. This is nothing but ionization enthalpy. This is nothing but ionization enthalpy. Okay. Now come to chlorine. First, chlorine is in Cl2 form. What we'll do, we'll atomize the Cl-Cl bond. We'll break the Cl-Cl bond and we'll get a one chlorine. What are we doing? We are atomizing the bond. So we'll call it as atomization enthalpy. From two chlorines, we are getting one chlorine, and how much moles we are taking? Half mole. So the enthalpy will also exactly be half of the 1 mole enthalpy. Okay. Now, after getting the gaseous ion, what we'll do, we'll convert the chlorine into Cl minus ion. That means we are adding an electron to chlorine. What is this energy called as? Whenever we are adding an extra electron to the atom, that is called as what is called electron gain enthalpy. Okay. This is nothing but our electron gain enthalpy. So this is how we'll be dividing the complex reaction into single stepwise reaction, and then we'll be adding all of them, that will be equal to lattice enthalpy. So see here, lattice enthalpy is nothing but summation of formation enthalpy plus sublimation energy, sublimation enthalpy for sodium and ionization enthalpy for sodium, plus atomization enthalpy for chlorine and electron gain enthalpy for chlorine. That is what we'll be seeing. Nothing but sublimation enthalpy of sodium and ionization enthalpy of sodium. Afterwards, we'll be adding atomization enthalpy of chlorine gas and electron gain enthalpy of chlorine gas. Why we took half here? So as we are calculating for half mole only. Now, if it is for 1 mole, we'll be directly take as atomization enthalpy itself. So you need to see how many moles. Generally, we'll be calculating these enthalpies for 1 mole only as per definition. Now, this is all about Hess law and Born-Haber cycle. Are there any doubts in Born-Haber cycle? If you have any doubts, try to mention in the chat. If you don't have any doubts, let's quickly summarize whatever we have discussed till now and ended up with Born-Haber cycle, which is the important concept to do many questions. Okay. So to do Born-Haber cycle, you need to know what are these enthalpy of combustion. We already discussed this. What is enthalpy of combustion? I think when we are combusting a organic compound or inorganic compound, that to exactly 1 mole in excess of oxygen. That is nothing but enthalpy of combustion. How much energy is released when we are combusting a mole of substance in excess of oxygen. Enthalpy of atomization is nothing but whenever you are exactly how much, let's say NaOH is there. There are 3 atoms. We need to make separate atoms NaO and H. How much energy is required to break all these atoms? Exactly 1 mole of substance, that too That is nothing but enthalpy of atomization. What is bond enthalpy? Nothing but how much energy is required to break exactly 1 mole of bonds of NaCl is there, let's say. And how to, if you are going to break Na and Cl bond, we need to provide certain amount of energy, right? Now, for exactly 1 mole of compound, how many bonds are present? Exactly 1 mole of bonds are there. So to break that many 1 mole of bonds, how much energy is required? That energy is called as bond enthalpy. Okay. What we write generally, enthalpy of a reaction is nothing but bond enthalpies of reactant plus bond enthalpies of products. Now, lattice energy. What is lattice energy? Nothing but energy required to break 1 mole of ionic compound into gaseous ions. That is nothing but lattice enthalpy. What is enthalpy of fusion? Nothing but enthalpy change accompanies melting of 1 mole of a solid substance at constant temperature and pressure. Clear, everyone? Enthalpy of solution. Next, enthalpy change when 1 mole of substance dissolved in specified amount of solvent. These are things we discussed till now. And at last we have seen nothing but what is enthalpy of solution. It is summation of lattice enthalpy plus hydration enthalpy of cation plus hydration enthalpy of anion. Now, how do we find lattice enthalpy generally? By using Born-Haber's cycle will be indirectly getting lattice enthalpy. So we have seen, right? Any one of this, like say lattice energies he's asking, then that means he'll be giving all these values and he'll be asking lattice enthalpy. Or he may not give electron gain enthalpy and he'll be giving lattice enthalpy and all these values, and you need to find out electron gain enthalpy. Simple questions will come, not too hard. Now these are some reference questions. Try it out in your workbook and in NCRT exercise. If you understood the concept, you'll be able to clear these. Now, try to do this question. Calculate enthalpy change of the process. He gave certain values and is asking enthalpy change of the process. Nothing but enthalpy of reaction, right? Okay. I think you tried what is given and all. So let's see what is happening in this equation. What is happening? He gave us CCl4 in gaseous phase and he's saying that carbon and 4Cl are formed. What is doing? He's atomizing the molecule, right? Now, he gave also calculate bond enthalpy of CCl. He's asking what is the bond energy of single carbon and chlorine in CCl4. Okay. What are the values he gave? He gave vaporization enthalpy. VAP means nothing but vaporization enthalpy. What is vaporization? Nothing but from liquid to gaseous. What does that mean? He's saying that CCl4 is in liquid state initially, and this liquid is converted into CCl4 gas. Now, this energy is nothing but delta H vaporization. Okay, enthalpy of vaporization. Now, okay, fine. He gave the vaporization enthalpy, and then he is saying formation enthalpy from carbon and 4Cl is minus 135.5 kilojoules, exactly opposite of this reaction, right? So what you need to do, exactly right, minus delta HF. We are writing exactly opposite reaction, right? It is like decomposition reaction, exactly opposite to formation, right? Minus of delta HF, that value. Clear, everyone? Now, after this, what is happening? He's saying that atomization enthalpy is also given. Atomization enthalpy is also given. For carbon, it is delta AH naught, and for chlorine, it is okay. 1 second. Let me clear this once. No, carbon will be given in form of solid and carbon will be given in form of solid and chlorine will be given in form of gas, right? This is what we'll be seeing, 2Cl2. Now what we'll be doing, we'll be converting carbon into carbon gaseous form. This is nothing but atomization of carbon. Now, chlorine will be converted into Cl, that is 4Cl, gaseous form again. This is nothing but atomization of chlorine. These are the energies he gave and is saying, what is the bond energy of C and Cl? Simple, right? All are given. What we need to do, find out the bond energy. Let's see stepwise. First thing, what we have, vaporization, formation enthalpy, atomization of carbon, atomization of chlorine. This is the main reaction what we need to see. Now, divide this reaction into simple terms. From gas to liquid, as it is opposite of vaporization, I'm writing as minus delta H vaporization. After that, what I'm going to do, I'm going to atomize the reaction. That is nothing but I'm going to simplify the reaction. Exactly opposite of formation reaction, where carbon solid is the starting point and chlorine gas is the starting point. That's why again I'm using minus here, exactly opposite of that. Now, after this standard substances are formed, I'm going to atomize carbon solid into carbon gas and chlorine gas and into chlorine atoms, from molecule to atoms. Okay, this energy is nothing but atomization energy of carbon, and this energy is nothing but atomization energy of chlorine. Clear? What we need to do? Add all these reactions. Delta H reaction is equal to minus delta H vap minus delta vaporization energy enthalpy minus delta formation enthalpy, and carbon it is 1, so it will be 1, but chlorine is 2 and 4 bonds. Okay, now add up all the equations. What you'll get, delta H of reaction is equal to minus delta H vaporization of CCl4 plus minus delta H formation of CCl4. Why we are writing minus? The only thing is we are writing exactly opposite of the formation reaction. That's why you have going minus delta H. The enthalpy will exactly opposite of formation. Okay, then atomization of carbon, and then 2 into atomization of chlorine, as we are breaking 2 chlorine molecules into 4 Cl molecules. Clear everyone with this? How we are writing this formula? If you have any doubts, try to mention in the chat. Okay, if you have no doubts, let's move forward. No, if you add up all the values which are given in the question, you'll get the value of total enthalpy of reaction, where you are converting CCl4 into carbon and 4Cl. That means you are getting the energy of 4 carbon chlorine bonds. Okay, energy of 4 carbon chlorine bonds. If you want to find out energy of 1 carbon fluorine bond, divided by 4. Okay, this is nothing but the energy of 4 carbon chlorine bonds. If you want to get single carbon chlorine bond energy, divided by 4, that will give you 326 kilojoules per mole. Okay, clear with this problem? Any doubts? This is all about Born-Haber cycle and all the enthalpies which we are talking till. Next, we'll be discussing entropy and second law of thermodynamics more detailedly. Okay, and after that, we'll be seeing relationship between enthalpy, entropy, and spontaneity or Gibbs free energy. Will be seeing. Next, we'll be seeing spontaneity. If you have any doubts till now, you can ask in the chat. If not, you can leave the meeting. I'll be launching a poll. Try to answer it. If you have any doubts, try to mention it in the chat. Answer the NPS poll and can leave.